So I want to talk about the C++ programming language for just a bit, because C++ plays a really important role in the development of object-oriented programming. C, of course, came out like 72 through 78, and then C++ came out in 80, and then both C++ and C co-evolved through the early 1980s. And then you see things like C# and Java and Python and PHP all informed heavily by C++. If we look at how object-oriented was happening kind of before C++, it was like C++ wasn't really appreciated by the typical mainstream procedural programmer of the day. And so things like Algol and Simula, it was kind of like there were tribes that liked procedural and tribes that liked object-oriented. But then C++ came along and sort of pretty much unified it, which meant that you probably learned Python as your first programming language, and you were using object-oriented programming from the time that you started. And C++ is what sort of unified that. And it was the C++ as the quickly #1 procedural programming language, and then C++ as the #1 object-oriented programming language that kind of brought order to the notion of procedural, object-oriented, hybrid, etc. And sort of everything that kind of came after 1980 was really strongly influenced and informed by C and C++. So let's take a look at how this sort of changed over time by looking at some syntactical influence. So C++, which was the earliest, which is a preprocessor plus a compiler, it turned into a compiler on its own eventually. But it has this concept of a map that has a separately selectable type of the key, type of the value, and it uses the square brackets, map, open square bracket, z, close square bracket equals 8. And that is in effect a put, right? That's like an insert into the map or update of the key, and it's a pretty succinct syntax. And so Python came up with a way. Python really didn't want to make a more complex syntax than C++, so Python worked on its language to make it so that you could just say D equals DICT, and it was a typeless language, and so we don't care the fact that it's going to be strings mapping to integers, because you can map lots of things to lots of things in Python. But it did follow the D sub z equals 8. And again, you used this from the beginning when you first started programming in Python, and you thought that was just natural. But what's really going on is more like what Java did in 1995. We're not going to use the square bracket to put stuff into a map. We're going to be more pure here, and we're going to create methods. Now, if you look under the covers in Python, you see that that is really a method that does that insert of the key of z and the value of 8. But if you look at Java, it says map string integer. So we again have this notion of a generic class, capital map string integer, map, which is our object variable, equals new tree map string integer, which of course is choosing the underlying implementation. And then they have the syntax of a setter style, map.put. And then they're giving the key and the value as two different parameters. There's choices that each of these languages are making, and I'll try to highlight them as we go through it. I want to talk a little bit about how C++ and its object-oriented approach and design made it so that a class like the map works almost the same as like a sort of a low-level class like a float or an int, and has access in particular to kind of the special characters or operators like square brackets or plus or minus, how that happens. And it is that you can create a specially named method inside of a C++ class that the compiler will consult and call when it encounters certain what you think of as language syntax. Meaning that as it's parsing the language syntax, like square brackets, it's like, oh, I've got some code to do some work here. This concept is called operator overloading, meaning that the behavior of the operator is controlled by the writer of the class. You are writing a class. So in this bit of code here, I've created, for no particular reason, a class that I call 10 integers in a row. And I have an array of 10 integer values, but that's private. So that's something that the outer class can't talk to, right? So you can't say 10 int 10 like in the main, 10 dot values is like, no, you're not allowed to touch that because it's private. But then what I do is I create a public method, which is the square brackets operator method, the method to be called when the compiler encounters square brackets, my class name, my object name, followed by square brackets, call me. Now the first thing we see is the return type of this operator, square bracket operator code, is an integer reference, an integer that can either be read or written, which means it can be on the left or right hand side of an assignment statement. And the parameter that it's being given is an integer index, which is the thing inside of the square brackets. Now, it is a reference because of the ampersand, but it is a constant reference, meaning we're not allowed to change it inside of this function. Okay? So const means we're leaving it alone, which means we're not allowed to say index equals 42 inside the square bracket operator method. And so what we're returning is that private variable values sub-index, but we are returning a reference to it. So wherever it appears in the original C++ code in the main, what happens is that reference can be, like I said, on the left or right side of an assignment statement. So let's take a look at how this works in the main code. I am going to create a variable called 10 of type 10int, and then I say 10 sub 1 equals 40, which means I'm storing 40 in position 1. But when it sees that 10 sub 1, it says, oh, this little class has an operator, square bracket operator, so I better call that little method, pass the 1 in, then that returns a reference to values sub 1, and then into that reference the 40 is assigned. Now Python doesn't have return a reference, and it doesn't have a call a reference. C kind of does, but they're pointers, and so references and pointers are different. References, you'll notice there's no special syntax to dereference a reference, whereas when you get a pointer, you got to have special syntax to dereference a pointer. So this notion of call by reference and return by reference is like impressive in C++ and allows it to do a lot of things and allows us to have this seemingly native line of code 10 sub 1 equals 40, which is really just a bunch of method calls. Amazing. And then we immediately say print 10 sub 1 contains and then 10 sub 1. And again, this is kind of a right-hand side of an assignment statement. It's looking it up. It calls the method, the operator, the square bracket operator method, passes 1 into it, and then we return value sub 1, and then that's what gets printed out. And so then we say 10 sub 5 equals 10 sub 1 plus 2, and now we see 10 sub 1 on the right-hand side of an assignment statement, which calls that same code in the operator brackets method within the class, passes in the 1, returning the reference to value sub 1, but then that reference is just 40, and then we add 2 to it, and then we assign it into 10 sub 5, which is again calling the int operator method to get a reference to values sub 5. And that assignment happens. All I really did was kind of faked it, but I used it to show you this like lovely ability to do operator overloading. When I first found my way into Java, my greatest disappointment, because I taught a C++ class and then I learned Java. I wasn't a whiz at C++, but I really thought it was pretty elegant. So for me, my brain was, so I didn't learn Python first. I learned C++ first. And I'm like, hey, that's what object-oriented ought to be. And then I'm looking, go in Java, and Java didn't do that. Java basically does not want and did not want as a choice to take values by reference in method calls, and even more, it did not want to return references in the return values of method calls. Those two things, the ampersand in the return type and the ampersand in the call, parameter call, those are essential for C++ to accomplish this. And Java did not want to return references, in particular because it has to do with garbage collection, variables going out of scope, etc., etc. And if you return a reference, you don't know when it's out of scope, etc. These are powerful, complex, and potentially quite dangerous things, right? But the C++ design was, hey, you are a samurai warrior, and you are going to use these very wisely, and we don't want to take power away from you. We want to give you all the power that you might want, and just trust that you're not going to make mistakes, right? And so choices that Java make and Python make are like, no, 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 we don't want you to make mistakes, so we're not even going to give you this kind of thing. There are other ways to do everything. Things like tuple returns in C is a good example of kind of an homage to this notion of returning things is not always just a single thing. So, but C++ is kind of unique. Now, again, Python emulated the C syntax that was quite beautiful, that was a result of C's support for operator overloading. And here's the thing where like it all comes together. So Python saw the beautiful syntax that C++, when you did the right things, the compiler would give you this, let you use this beautiful syntax and still call your methods inside the object. But they didn't want to do the call by reference and return reference that C++ did. And so what they did is they did basically a syntax transformation. If you look, Python is in a sense very Java-like in that everything has to happen through methods. But then there's these hidden methods. Okay, let's take a look at the code. So I'll create a dictionary named X, and then we say X sub 1 equals 40. And again, we know what this means. That means somewhere in the key, under the key 1, there's 40. Now, I can print this out by saying X dot double underscore get item double underscore open paren 1 close paren. That's taking the index inside of the square brackets and passing it to a predefined Python understood rule for what get item, the square brackets turn into double underscore get item double underscore, where the X is the object and the parameter is the syntax. So if we think about it on the right-hand side of an assignment statement where we're just reading it, it's just doing a get, right? It's kind of doing a getter-like thing. Give me item 1, and then out comes the 40, and that's how the print of X sub 1 is a 40. That's really what happens. Under the covers is there is a class which has underscore get item underscore defined in it as a method, and that's how it loads X sub 1. So if we go down another line and we say X sub 5 equals X sub 1 plus 2, seems simple enough. And literally for years, Python software developers don't even need to know that this is miraculously and beautifully complex. But what this translates into at runtime by compiler syntax transformation is the X sub 1 on the right-hand side turns into a X.getItem paren 1, which pulls up the 40, and then plus 2 gets added to it. But then that expression is passed into X.setItem in position 5. So the left-hand side of the assignment statement is the X sub 5 equals part, and that's calling setItem. So if it's doing a square bracket lookup on the right-hand side, it's calling getItem. And if it's doing a square bracket on the left-hand side of an assignment statement, it's doing a setItem. So this means that there was no need to return references, no need to process references, none of the hoops that C++ went through. And so you see that Python did not choose to implement the way C++ did, but they supported the very elegant syntax. Now, and then you'll see that Java in 1995 takes it, or 94, takes it one step further in that they're not even going to give you that cool syntax. They're like, no, we're going to say just do x.put and x.get and call it good. If you know that x is an object and you need to do a get and a put, do the get and the put. We're not going to do this little syntax transformation that makes it pretty. And we're also not going to give you operator overloading because, again, operator overloading requires references because it allows the class to return a thing that can be used on either the left or right-hand side. And again, Java did that because they did not want to make their memory management more complex. So it's a hard to argue. But what this kind of shows you is like the amazing interplay between these languages. Bjarne Stroustrup went to school in Denmark and started working on C++ in Denmark, but then was hired to go to Bell Labs in New Jersey, where he met and worked with for a number of years. Bjarne Stroustrup and Dennis Ritchie and all the folks at Bell Labs that gave us Unix and C over the decades. And so C++ kind of came to the world from Bell Labs, from Murray Hill. And Guido van Rossum, who was in Netherlands at the time, really was just looking at all this stuff and using all this stuff, and an expert in C and C++. And back in those days, we tended to look a lot at like the code that C++ generated. And Guido's like, I'm gonna borrow. These are really good patterns. And so that's how we see so much influence of not just the syntax, but the actual runtime conventions. And like, if you look at some of the generated C++ code, the concept of private is often done with underscores. They use underscores a lot. Python's like, yeah, I'll just borrow that. I'll just use double underscore as my signal as this private, and away you go. So to show the influence that C++ and C had over Python, both in the syntax and in the runtime, we can take a quick look at some internal details of how Python works. And Python turns out to have almost identically implemented operator overloading as C++, but we don't see it. It's all internal. You have to kind of look. So on the left-hand side, that's the code that I just got done going through. That's the C++ code that has the private values and then the public operator overload. And now if we look on the right-hand side, we see a class 10int, and I'm creating a double underscore values, which is values private, as a dictionary. And then I'm going to define the set item. So this is like a private method called setItem, and then a private method called getItem. Python basically has the left side and right side assignment of bracket lookup operators different. And the setItem is the left-hand side, and the getItem is the right-hand side. You'll see that in the setItem, I'm just taking self values, subindex equals value, and I'm in the getter, I'm returning self underscore values subindex. So that's the right-hand side. So if we look at the code, I see, let's make a 10int on the variable 10. 10 sub 1 equals 40. Now Python transforms that 10 sub 1 syntax into a set item of 10, comma the number 1, comma 40, and then calls set item. And you can see, of course it worked, right? The three values are self, index, and value. Well, self is 10, which is the object instance. The index is the thing inside the square brackets. And the value is the result of the expression on the right-hand side. It's not just 40, but it's the expression on the right-hand side. And so that goes in, right? We see the print. 10 sub 1, well, that is a right-hand side reference to 10 sub 1. So that's going to call getItem. Self is 10, and then index is the 1. And we're going to just return it, and that's going to print out a nice little happy little integer, which is exactly the variable 40. So it says 10 sub 1 contains 40. And at this point, it should be obvious what's going on. When I say 10 sub 5 equals 10 sub 1 plus 2, well, the 10 sub 1 on the right-hand side turns into a getItem that gives us back the 40 value. Then the 40 and the 2 are added together to finish the right-hand side of the expression. Then we're going to assign that into 10 sub 5, which then turns into a set item of 10, comma 5, comma 42. And then that stores 42 in position 5 in our private variable values. Private values variable. And then I print it out, which is a left-hand side lookup of 10 sub 5, which calls getItem again with self is 10 and index is 5, and so we get the 42. And so you see how they're so similar inside. I mean, again, like if you look at generated C++ code from early C++ code compilers, you'll see these double underscores used in various places, which means that Python in its internal implementation used the same patterns as C++ did in its internal implementation. Python chose not to do call by reference and return by reference. Java chose not to do call by reference and return by reference, and Java chose not to do the fancy syntax transformation. But who knows? Maybe one of these days Java could do that syntax transformation and be like, whoa, Java has everything. And then to some degree, Python has shown the way about how you do this without doing call by reference. And again, that ampersand operator and ampersand index on the left-hand side, that's the scary part where language designers are like, I'm not sure I want to go do that, because C++ is not a garbage collected language, but Python and Java are garbage collected languages. And that's not the only reason that Python and Java didn't want to do call by reference, but it is one of the reasons that you it just simplifies to know that when a function is done, it's done, and there's not sneaky little pointers inside that function that need to stay alive. So it allows you to throw stuff away when functions are finished. Okay, enough of that. Just again, I'm just trying to show you in the simplest possible examples the kinds of design decisions that all these language and library designers were doing as they built the languages that we know, love, and use today.